Good evening, everyone, and welcome. I am Gabriele Serra, a first year PhD student from Scuola Superiore Sant'Anna of Pisa, and I will present our work on architecture for declarative real-time scheduling on Linux. Okay, so I want to start talking about the context. Real-time systems today are in practice everywhere, and in the past decade we saw a rising interest in the topic of running real-time applications by deploying them directly on general purpose operating systems. Linux and derived operating systems are a common choice for non-safety critical application, especially when they must support a rich set of multimedia peripherals, also thanks to the number of libraries and tools that have been developed. During years, Linux has been improving its support for real-time. In this slide, I have reported a timeline that shows, let's say, the most critical patches that have been made to the kernel to extend the support to real-time computing. I want to stick analyzing checkpoints all by one, but however, the most recent was the merging mainline of the sched deadline policy that implements an ADF scheduler based on the CBS algorithm to provide a temporal isolation among tasks. Much effort was placed by this community, the community in general, but this community, to increase the relevance of Linux as a suitable platform to develop real-time application. But work focused not only on the kernel, but let's see something more. Historically, one of the most exploited technique was to add a real-time microkernel between the hardware and the Linux kernel and run Linux as the lowest priority task, leaving the management to the real-time microkernel. In practice, the approach was, let's say, to rely on a distinction between the real-time tasks and the leftover. Here in the slide we can see the real-time microkernel placed between the hardware and the Linux kernel. Okay, through the years also real-time extension was developed for research purposes or experimental prototyping. Maybe the most notable example are Litmus RT or Cart Linux. Litmus RT maybe is the most relevant one and consists of a kernel patch which communicates with the user space and allow application to ask for real-time tasks to be scheduled, collocating, let's say, with this patch. Another example is the DIAcosa framework. Recently, also many middleware were released. Here, a representative, let's say, example is the FreshForb. That is a middleware based on Corpa and lets real-time application to create a kind of reservation across not only the CPU but also disk and networks. Anyway, it relies on an extension of the Linux kernel. Most of the solution we have seen here, let's say, relies on a single real-time scheduling strategy. But interactive or multimedia workload need a variety of different tasks and with heterogeneous temporal characteristics. Also, platform nowadays are multi-core platform. So it is all but trivial to understand how can this application coexist in the same system to exploit the different underlying schedulers offered by the kernel, and also how to configure this scheduler offered by the kernel to work in optimal way or suboptimal way on a multi-core platform. The current approach does not scale well. It needs skills in configuring the system to work, and furthermore the system admin can often know a priori the priority of application or PIDs of application. Therefore, we let's say propose a novel framework that can be used to declare the temporal characteristics of a real-time application, but without enforcing the use of a specific scheduling technique. So let's forget about it. Our proposal is the real-time system daemon, a declarative real-time scheduling approach, where application can simply declare a set of timing characteristics and scheduling requirements, such as the runtime or the periodicity, or also the request of a specific kernel plugin, and then they do not have to worry about the techniques that will be used to match the attributes. Okay, how to achieve this goal? The proposed frameworks in practice adopt a modular architecture. A set of plugins are used to translate the attributes declared by each application to proper kernel configuration. And this modularity offers a set of features because APIs are independent of available kernel policies. Schedulers can be partitioned over different CPUs, and the framework can be installed over an unmodified kernel because plugins relies on policies offered by the native Linux kernel. Also, application without root privileges could access to real-time policies. Plugins, as said, the framework, let's say, is independent, offered an independent API, so you can port the framework onto different operating system, simply substituting the plugins. Okay, so let's start to analyze each module one by one. Application that want to use to leverage on real-time capabilities can communicate with the daemon through the RTS library that in practice is a shared library linked with the application binary. And the library offers an API to, let's say, create, modify, and delete logical real-time task, and further to attach a flow of execution through the logical real-time task previously created. In the slide here, here in the slide, I have reported the parameters you can specify with your application, such as runtime, desired runtime, the period, the deadline, the priority. For instance, in your application, you can declare only the periodicity, maybe, and then it is enough to schedule your application with the rate monophonic plugin. But maybe you know also the runtime. So you can declare the runtime and the periodicity, and maybe you can specify that you want to schedule your application with ADF, and so the daemon will schedule your application with the ADF. But maybe let's think about a Linux kernel that is an old one and do not have the ADF scheduler, and then maybe you can trust the rate monophonic plugin. So all these cases are covered by the framework. Okay, the essential component of the architecture is the central decision authority, that is the daemon. and this component can connect and coordinates all the interaction among application and plugins. And in practice, when a task arrives, the daemon interrogates one by one each plugin and then select the plugin which fits better the requirement of your application. And then, of course, it sends back the response. Okay, so let's analyze the last piece of the framework, plugins. Each plugin must implement a set of functions that are used by the daemon to dispatch requests, and each plugin supports one or more scheduling policies offered by the kernel. Also, each plugin may implement an admission control mechanism that can be used to check maybe if a new task can be admitted or not to the current task set. And currently we made available the ADF plugin, a rate monotonic plugin, a fixed priority plugin, and a round robin plugin. We are working on a sporadic server plugin that will be based on the POSIX sched sporadic that on Linux was made available through the patch written by Fagioli, one of our former colleague of the laboratory. The ADF plugin supports the sched deadline algorithm and implements an utilization-based admission test. Tasks that are accepted are scheduled following our worst fit policy, namely are assigned to the least loaded CPU. The rate monophonic plugin, on the other hand, supports the sched FIFO policy, and the load on the CPU is estimated with the CPU utilization, of course when possible, but because maybe tasks are, let's say, have not declared the runtime. Of course, priority is assigned in inversely proportional manner to the period, and we have made a decision to assign task following the worst fit policy also here in the rate monotonic plugin. Okay, in this slide I have reported an example, a code sample. Maybe could clarify the concept. Let me take the laser. So in the first part, the task declares its parameter, and then he tries to create a test to, let's say, create the logical task. If the test is let's say passed on success, we can attach the current flow of execution through the logical task created. Then in your, let's say, cycle, you can do your mandatory computation, but if you have some of spare time, because you are, let's say, the daemon accepted your desired runtime, you can do also optional computation, and then of course you can finish your period. Okay, so let's pass to the performance evaluation. Briefly, these are our environment characteristics. We have an i5, we have tested on i5 desktop computer, and here are, let's say, resumed all the parameters if you want to repeat the test. Okay, so the benchmarking application is a single-threaded process that performs multiple requests to the daemon, each time adding a real-time task to the task set, and we want to evaluate the cost of the task admission test performed by the ADF plugin and the rate monotonic plugin. Here in the slide I have reported the results. You can see the minimum average round trip time is 16 microseconds. So from the plot it is clear that while the response of the ADF plugin is constant, the rate monotonic plugin has an increasing cost that can be attributed to the operation performed by the plugin to update the priorities assigned to the task. But for both the plugin notice that the cost must be paid only when declared a new task, when a new task joins the task set, because during the regular scheduling operation, the overhead introduced is zero, because you use directly the policy offered by the kernel. Okay, so first I would say that the realization of this framework was motivated by the recent advances in the kernel feature that, in our opinion, need to be followed by corresponding advancement in associated middleware and also user APIs. There are a lot of future direction. We want to improve the daemon. We want to work on supporting power management techniques and also heterogeneous architecture. If you have a big little architecture, for example, um, we want to, let's say, support this kind of cases. So I can say collaborations are welcome. So if you want to contribute, here you can find the repository, the GitHub repository. Send me an email and we can talk about it. And that's all. I want to thank you for your attention. I hope you have appreciated this work. And if you have some question, feel free to ask during the Q&A session. Thanks.